Good morning, everyone. Well, it's a little bit too early and a little bit too virtual for some of us, but I'm extremely happy to be here to celebrate Professor Ravi-Chandar's career in the form of the Prager Medal. I don't want to take too much time from Ravi's presentation, but I do want to make a few relevant remarks, some personal and some that I heard repeatedly from many colleagues in the community. As you probably know, Ravi graduated from Caltech in 1982. He worked with Wolfram Canaus, and after graduation, he went to the University of Houston. And in the year 2000, he moved to the University of Texas at Austin, where he is currently and holding an endowed chair position. I was trying to think of how to, describe Ravi's contributions and Ravi's career in a nutshell. And I thought that perhaps a good way to do so is to paraphrase a colleague who said that Ravi is a modern Da Vinci of experimental mechanics. And this is because he has looked at a variety of topics of fundamental importance. And every time he does that, he gets into a problem. He does so in a very unique way that is very refreshing, the way he thinks about them, and they're very inspiring. And then there's something special about the way he looks at mechanics problems. It's fair to say that his interest in mechanics is broad. He cares about all problems in mechanics, but perhaps it's also fair to say that fracture has a special place in his heart. And there he has contributed, significantly in a variety of topics, ranging from dynamic fracture to fragmentation in ductile materials to, more recently, cavitation and healing. On a personal note, I like to add that, I have had the privilege of working with Ravi, over the last 9 years. And it has been extremely enriching experience, not only because of the technical aspects, and the passionate discussions that we have had. I guess he may want to comment about those if he wants, but more so also because of the personal aspect. I think Ravi is a true gentleman who deeply cares about the mechanics community, and as he has demonstrated in the many service roles that he has played and continue to play. So for all of the above reasons that I tried to quickly summarize, I think that, one could argue that Ravi is the perfect embodiment of the Prager medalist. And on that note, I finish this introduction, and Ravi, the floor is yours.
Thank you, Oscar. I'll try not to believe everything you said. Let me share my screen. And okay, I guess you see my screen and a video feed. Thanks for the kind words and the introduction. I want to begin by thanking the SES Awards Committee and the board of the SES for giving me this great honor of the Prager Medal. This is particularly special for me because as I began my career, the very first presentation that I made in a conference was at the 16th SES in Evanston, Illinois in 1979. And I've been participating in SES ever since, roughly half of all of the meetings that I've attended. I want to thank Oscar and the letter writers for putting this thing through. It means a lot to me to be recognized by colleagues for things that I have done as I enjoyed them along the way. Also want to thank the people that are going to participate in the symposium today. These are the speakers to follow mine, and I hope I'll finish in time to allow them full time to present their work. I appreciate their participation very much. I'll have more to say about all of these on a personal level at the reception this afternoon. But now let me start with the technical presentation that I had decided on. As Oscar pointed out, I have tried to do through experiments a number of different things. And here is a collection of topics that I have worked on over the nearly 4+ decades of involvement in mechanics. I'm going to highlight 3 of these: dynamic strain localization, ductile failure, and cavitation and fracture. There are a couple of things running through all of these things. Every one of these has underlying it some experimental component. All of these start with some newly or improved design of an experiment that reveals something about how things happen, whatever the things are that we may be interested in. Creates them in a laboratory, diagnoses what's going on, and presents a picture that can then be used in developing models and simulations. That's been the running theme behind everything that I have worked on. And it's been a fun journey, because every time I get to design and run a new experiment, it's just pure joy. Experiments have been around for a very long time. And I want to start on experiments by a story from an Indian parable of the 6 blind men looking for information on an elephant. And I'll provide this in a modern context. So these 6 blind men are restricted in the sensors and diagnostic tools that they are able to implement on the experiment itself being seeking knowledge of an elephant. Deprived of eyesight, they use their other sensors of touch, feel, and each comes up with a particular picture model of what an elephant is like. One thinks it's like a pillar, one thinks it's like a rope, one thinks it's like a wall, another one like a spear, and so on. They're each convinced that their model is right. And when they get together for their verification and validation meeting, they have a fight because each is convinced that he is or she is right. What is needed here, of course, is more diagnostics. So they go for an arbitration to a prince. He has other sensors, is able to see a bigger picture, more diagnostics, more information, better model. So he says, all of you are right, but all of you are not right as well because you don't have a complete picture. So what you need is more diagnostics. Fast forward a few millennia. The founding father of sciences, in my opinion, Galileo Galilei, is reported to have said something like this, although there's questions about that. Measure what is measurable and make measurable what is not so. That's the essence of discovery. If you do experiments and you instrument the experiments with suitable diagnostics, you can develop much more insight into the problem and develop models that are truly predictive based on that. There are other examples one can see about models and so on. Here's a starry field of the Leonids meteor shower. This picture can be interpreted, has been interpreted over millennia in many different ways, simply as an almanac, as a model based on geocentric, heliocentric, Big Bang, whatever you want. There's been a progression of models. None of these models is wrong, but they're not complete. Each one built on the other one and provided us with a better holistic picture of what happens. So the interplay between experiments and models is a very important one. And it's been expressed very elegantly by a number of people. James Bell indicates that the agreement between, or a correlation between data and prediction doesn't necessarily imply that any one set of assumptions is correct or any one model is correct. You have to keep refining your measurements, you have to keep refining your models until you come up with acceptable models that predict in reasonably meaningful way. But that means there's a plethora of models around for the same experiment. And the question is, what guiding principles should one use? This is also the topic that's been in the realm of philosophy for many decades, many centuries. The first and perhaps the most elegant way in which this is represented is called Occam's razor. Occam was an English friar in the 13th century thinking about formulation of ideas. And in a cryptic way, he says entities are not to be multiplied without necessity. And all it says is if you have a model, make sure the number of degrees of freedom is small. Smaller the better, because if you, the likelihood that that model is right is larger. Fewer sets of parameters predicting a larger set of responses or outcomes. So I've taken, in doing experiments, I've taken a number of these ideas into consideration. Occam's razor, make the simplest possible model to be able to predict whatever phenomenon you want to predict. Galileo's idea that you need to instrument it and diagnose with as many measurements as possible. And I want to illustrate this with a few examples. The first one relates to dynamic strain localization and fragmentation. And the key participant here is Haitao Zhang, who was a postdoc with me for a number of years. And we wrote a few papers on this topic. It's a problem that arises in a number of applications in impact, blast, and high-speed metal forming, and so on. The main idea is for a ductile metallic material, if you do a quasi-static test, pretty much everybody knows that there's an inelastic response followed by localization at the considier strain, and beyond localization, the bulk of the material or specimen doesn't deform, only the localized region deforms further, leading to eventual failure. So the question that people raise is, what happens if the strain rates are large? Strain rates not quasi-static on the order of 10⁻³ per second or so, but 6 to 8 orders of magnitude larger, 10⁻³ to 10⁵ per second. There are a number of, basically, two things could happen: a necking of this kind here, or a sheet mode necking of this kind, where it thins in the third dimension but has a band at different orientations depending on the plane stress, plane strain constraints of the body. There are a number of standard techniques for doing these kinds of experiments, and I won't go through the list of them. I want to highlight the electromagnetic loading because to me, it represents clean loading. It is a loading that arises without wave propagation. It loads through body forces, and the controls are done through electric currents. So the speed with which these things go are orders of magnitude larger than elastic wave propagation. So we decouple elastic and plastic wave propagation from the loading applied on the object. The idea is very simple. It was something that was introduced by Fridtjof Nansen in about 1960 or so. If you take a coil, electrical coil, and discharge a very large current through that, it sets up a magnetic field. If you now break that magnetic field with a thin ring, which is our specimen, a conducting material, it generates an induced current by breaking that magnetic field. The induced current is in the opposite direction to the running current in the coil. The electromagnetic interaction between the two results in a Lorentz force of repulsion between the two conductors. The coil itself is held fixed inside a very stiff housing, and so it doesn't have the ability to move. But the specimen is free, and so it wants to get away from the coil, and it expands out radially, symmetrically, and in timescales of 10 to 50 microseconds, the object strains to strain levels on the order of 20 to 30%. Strain rates are on the order of 10 to the 3 to 10 to the 4 per second. The important thing is it's a body force loading There are no stress waves necessary to generate the modes. Over the years, there have been a number of different ways of instrumenting this. The most common one is to measure the currents flowing in the two, in the coil and in the specimen. And these are the measured values of the current. They are on the order of tens of kiloamperes. So they're very large and potentially dangerous currents. But you measure them, you know the driving force, and so you can calculate what the response should be. And most commonly, they picked up pieces of the broken specimen and identified from that some average measure of strain. The innovation that we brought to this problem was to take this specimen, fix it in a housing such that there was a clear path to view coaxially with the coil so that you'd be able to see the ring. Place that in a high-speed camera in a shadow mode so that you could see a shadow of the ring and take pictures at high framing rates. So these are pictures that are taken once every 10 microseconds. This is a shadow of the coil and the housing. The specimen is at the outer perimeter of this. At the first frame, you see that there's uniform expansion of this. These are very high spatial resolution images that we can expand and see more detail. In the next image, the straining has continued, and you could see that the strain is more or less homogeneous around the entire ring length. And at this point, the ring has broken in multiple locations. But here's where Galileo's measure what is measurable comes into picture. This particular camera has a combined streak mode and framing mode, so it is able to time resolve things in a particularly interesting way. More than that, when the ring breaks, it's circulating very high currents on the order of tens of kiloamperes. So it is breaking a fuse. There's an arc that jumps across there. The arc creates a shock wave in air. The shock wave is visualized here through Schlieren images that are a part of the aperture of the camera. So if you work back from the wave speed of the shock to where the event initially occurred, you could find precisely the time relative to the time when the frame was taken, the time at which the first, second, and the third fractures occurred. They were independent of each other. You could convincingly prove to within sub-microsecond resolution that this fracture had no way of informing this fracture through any wave, elastic or plastic wave propagation mechanism to communicate to this. So these fractures occur independently of each other. You can also see there are other breaks in here that happen after, because there's no more arcing in these things. The currents have quenched, breaks occur without arc discharge. So you could rank order the order in which the various fractures occurred. And beyond this, the broken fragments simply move as rigid body, and it's not interesting. If you used any other kind of diagnostics on this, for example, you use a visor reflecting off of the surface of this thing, you would measure the velocity of this. This is a very common measurement, but it will give you the kinematics of the problem. It doesn't say anything about when the fractures occurred and what sequence they occurred in. If you take one of those images of the ring and expand it out, enlarge it to see more detail, you could see there are about 40 necks that form in this one particular experiment. Of those, the ones marked in red are broken at this frame. The ones marked in blue will break in the next frame. We know that because we have the next frame. And the ones that are marked without any symbols around them did not break, did not even proceed to full necking. They necked to some extent, but then got unloaded because the driving force was interrupted when the specimen broke. There was no more stress in the specimen. You could make some very interesting images out of this by doing overlays and tracking particles to see local velocity fields and things like that. Those are much greater detail. I'm just showing all of this to say how much information can be obtained from one experiment if A, the experiment is planned to be a very simple loading condition, and B, if the diagnostics are rich enough to be able to indicate multiple quantities about the same event. So from looking at multiple experiments of that kind, again, I'll come back to this at the very end. We had done on the order of 100 experiments of that ring expansion test in different materials to collect overall information about the response. And the order or sequence of events is very clear from this set of experiments. First, there's uniform expansion of the ring, just one-dimensional stress state, very easy to calculate the response. Then there's the nearly simultaneous nucleation of necking localization at multiple locations. If the experiment had been done quasi-statically, the first neck that forms would unload everything else and there would be no further necking. The dynamic body force loading, which strains each point independently, allows for this localization to occur at multiple locations. Each localization, as it occurs, unloads a certain domain. And so only some of these necks are able to progress, others are under diminishing loading. Some of those things go on all the way to fracture, but the other parts remain unloaded and they stay deformed and they provide more information about what happened during the fracture event. You could collect all these fragments and do statistics of the fragment distribution and so on. I'll get to that in the next few minutes. Analysis of this up to the point of onset of necking is very straightforward. First line says F equal to MA. The force comes from the interaction of the currents between the coil and the specimen. Its resistance comes from plastically deforming the material as it expands out. The second one is the rate of change of current, and this depends on the specimen moving away from the coil as a function of time. And the last line indicates temperature effects and so on. But you can solve this. This is a simple first order ODE. And by solving it, you can compare. The red line is the current that is supplied to the coil. The blue solid line is the current that is measured in the specimen. The dotted line is the current that is calculated by that one-dimensional model, and they agree until the onset of localization. So we can get a constitutive response of this thing until the onset of localization from here. You can also calculate the ring location or radius as a function of time, and this works even beyond the onset of localization, because beyond that it's just rigid body kinematics. But that's not the whole story. We need to know when it broke and how it broke. More diagnostics. And this time it comes not from the real-time imaging. These are evolutionary problems. Things happen as a function of time. And a record of what happened at an earlier time is left in the specimen after the test is over, if you're able to tease it out in the proper way. Actually, Mott, Neville Mott, who was a physicist who worked in some of these problems, explored this idea of the fragments, and he found constant strains in regions of the fragment, and he thought that the specimen had been fully exhaustion hardened and couldn't deform anymore, didn't have any strength anymore, and it broke at that point. But if you look at this, this is a piece of the ring recovered. I forgot to mention that at the outer periphery of our device, there was a very soft clay into which the specimen goes and launches itself and slows down. So we're able to recover those specimen pieces without damage. So if you look at one of those, this is a fragment which broke at both ends through a fracture process. But along the length of that, you see the width is not uniform. So if you measure the width of this and call that W of X along the length, you see there are regions in which this width is constant, which means it hasn't strained beyond a certain point. This is plastic deformation. It's incompressible. So if you use that, you can take that width variation and convert it into axial strain of the specimen at that point. And what it says is, in pieces of the specimen in between where the necks are, the strain is uniform. And the magnitude of the uniform strain can be calculated simply by knowing the width variation. And that width, that uniform strain is constant. This is in an aluminum 6000 series annealed. This is in the, this is in the aluminum 6000 series annealed. This is in a soft aluminum 1100, and this is in a soft copper 101. The remaining strain in the unnecked portions of these ring expansion specimens is exactly the same as the considier point in the quasi-static strain experiments. So what this says is, even under high strain rate loading of about 10 to the 4 per second, necking sets in exactly at the considier point. This is contrary to a lot of models that have been around and to a lot of calculations that have been attempted to extract strains from fragments, but I'll leave it at that. You can also get the statistics of the distance between the necks, and just by collecting all of the 100 specimens and sorting out their distances between necks and collating them with the speed with which the ring expanded or the strain rate. So the one corresponding to expansion of 80 meters per second and 200 meters per second are overlaid here, says that as the strain rate increases, there are more fragments, the distance between the necks decreases, and there are more necks in each one of the specimens. It seems this is driven purely by statistics. There are attempts to do linear stability analyses where you take the uniform expansion and perturb it with a sinusoidal perturbation over the entire specimen, watch for the fastest growing modes and say those are the ones that will dictate the spacing. If you compare with such analyses, so this is the neck spacing observed divided by the neck spacing predicted by a linear stability analysis, you should see a peak at 1, but more importantly, you shouldn't see large amounts of unnecked regions, which is what we observed in the experiments. So we've actually questioned the suitability of the linear stability analysis to be predictive with respect to neck spacing. I think it's more appropriate to think of a point perturbation and see how the point perturbation will propagate through the cross-section of the specimen. And we attempted this through a very simple numerical analysis. Take our specimen, do a 1/4 symmetry model of that, put a defect at one corner, and see how the defect propagates across the cross-section. And if you do that, the defect is at one corner, and it grows through, and the necking starts to form, but regions far away from the place where the necking initiates are able to strain to much higher levels, depending on the cross-sectional geometry of the specimen. So this necking strain is going to be something that is specimen size dependent, that comes purely from inertial effects. And for more details, you can contact me or I'll refer you to the papers. The next step in the same experiment is a innovation for looking at cylindrical objects. If you have a tube instead of a ring, it's difficult to diagnose this with the kinds of instrumentation that we have. Typically, we are restricted to watching from one side, a part of the cylinder, and post-mortem examinations. What we decided to do was to take the coil, slip this cylindrical specimen along the coil, build a conical mirror, place the specimen coaxially with the conical mirror so that if you view the camera on the surfaces of the conical mirror, we will see a projection of the entire surface of the cylinder. To make that visible, I'm going to use Andy Warhol's favorite object. There's the surface of a cylindrical object. This is the conical mirror that we had specially constructed using an astronomer's shop. If you look coaxially with the conical mirror, the entire surface of the soup can is visible on the polished surface of the mirror. And then you can do digital unwrapping of that and see every point on the surface of that cylinder. Just add a high-speed camera to it, and you get the ability to diagnose what happens on the entire surface of the cylinder. So this is the coaxial view. The cylinder is right around this outer edge. This is now a different high-speed camera, lower spatial resolution, but much easier to use. On the surface of the conical mirror, you see the surface of the cylinder. The cylinder was etched with a pattern of circles to be able to measure strains in post-mortem. And I'll play this video, and you can see the cylinder expands out. At some point, it fractures into multiple pieces, and you can see the sparks flying from the arc discharge. This is a deceptively slowed down experiment. The entire experiment took about 80 microseconds, but you can slow down everything with digital magic. All right, so you can then look at every frame, and you could see the onset of localization, the onset of fractures, and how the fragments form, and so on. I think I will skip these things. Again, post-mortem examination is important because it shows localization has occurred in multiple locations. They are of the sheet mode necking in this case. The angles are exactly what's predicted by Hill's quasi-static analysis for uniaxial tension. And so again, strain at onset is exactly what's predicted by quasi-static analysis. Strain rate effects in this particular material, this is a 6000 series aluminum alloy, don't seem to have a very strong role to play. You can construct dynamic forming limit diagrams from this, but I'll again skip that. One simulation to say very simple elastoplastic model, strain rate independent, but with a number of defects thrown in to create nucleation sites for these diffused necks that are formed everywhere, recreates patterns that are very similar to what are observed in here. There's not a quantitative match yet because we don't have a very good stress strain curve to go to strain levels that are seen in these objects, but that's a story for a different time. All right, that's the first story of dynamic strain localization. The second one is similar materials, polycrystalline materials, but now ductile failure at slow strain rates, commonly encountered in a number of applications of forming and things like that. There are two essential ingredients in making predictive models for these applications, plasticity and fracture. It turns out fracture is just the endpoint of where plastic deformation leads to localization. And you need to have very careful experiments to identify strain levels at which these things happen. Ductile failure immediately brings up this idea that there is void growth coalescence processes going on. And if you look at fracture surfaces, they do indicate that you have dimples on the surface, which are evidence of cavities that have formed and coalesced. The status of this has been captured in a couple of, or three different challenges that were presented by the Sandia National Labs to see if people could predict the response of different structural configurations given experiments for calibration of material properties of both plasticity and fracture. And what I show here is a collection of data. The gray lines here are the collection of experiments, and the various colored lines are predictions of the global force versus the opening displacement along the loading line as predicted by 14 different teams, and they're all over the place. This is a second challenge. There's a third one that's similar. It simply says that predictions are scattered all over the place, and it's not clear what the most appropriate model is to get prediction in these kinds of very simple structural problems. I started looking at this about 10 or 12 years ago, and we had this idea we need to look at locally the picture of what happens to plastic deformation and failure mechanisms in a variety of materials, both pure metals and metals or alloys that have impurities of various kinds. So we chose a oxygen-free, high conductivity copper, 99.99% pure. No alloying elements, no second phase particles, nothing. And the grain structure is shown here. They are kind of platelet-like grains that are oriented in the direction of rolling. On the right-hand side is a 6000 series aluminum alloy. This is age-hardened to T6, and so it has precipitates that are on the scale of the lattice level, but they also have second phase particles, some of which are identified here, that are bright white in this etched picture. Once again, you can see the grain size distribution. They're on the order of tens of microns. The volume fraction of the second phase particles is less than about 1%. These are hard particles, and they do play a role in how the material on the right deforms and fails as opposed to the one on the left. We do tension tests. Everybody does this to characterize material properties. But we did what are called interrupted tests. These are also were commonly used, but not so in recent years. The idea of an interrupted test is you run the test once all the way until failure, so you know what the global response looks like, for both materials. Then you run it to the peak load, unload it, put away that specimen. Run to another load level, third, fourth, fifth, progressively approaching failure, and unload them and examine the specimens that have been unloaded. The idea is this is again an evolutionary process. Something is going on. Both deformation and failure mechanisms start at some point and progress as you continue the loading. A trail of what happened there is left in the unloaded specimens. If you can interrogate them and explore them in great detail, you will learn something about what happens. So let's start with the copper. At the point A, necking localization occurs, but you really don't see any change in the structural dimensions of the specimen at large scales. At B, this is what the cross-section of an initially straight specimen looks like. This is the neck that has formed. And these are high-resolution microscopic images of the grain structure that have been assembled together into one piece. They're made out of 200 microscope images in one piece. These were done in the days when automatic stitching of these things were not available, but since that time, the technology has improved to do this in very short order. If you come to this point at C, the neck has developed more. And I'll expand this. This is why I needed a second screen. You can see greater detail. I will zoom into something here. This is an image of every grain at every point of the cross-section. And you can measure the dimensional changes. And you could see a lot of other features that I'm not going to outline. For example, these are streamlines of the flow that I can identify from this. Streamlines break the surface, which means there's been a discontinuous event taking place. But if you squint your eye, you could see there's the formation of the shear band, two intersecting shear bands in the plane strain region of this specimen. If you zoom in even greater to that, you could see at the center of the intersection between the two, there is a cavity. And this cavity is rectangular in shape. It has sharp corners. And to make that visible, take the same specimen and look at it under an electron microscope, you could see the corners that have been formed. So it's breaking in a very, very weird way, is one way to put it. It's creating rectangular corners inside of a material. If you continue loading to the point D, that rectangular cavity remains a rectangular cavity and enlarges inside. So there's some interesting mechanism that is underlying that. If you slice that perpendicular and go in the third dimension, it's a tunnel. So this rectangular cavity is a prismatic cavity that forms along the width direction of the specimen. Finally, when it breaks up at the point E, it forms two wedges. These are not cup and cone fractures. You cannot put them together. A cup and cone will have mating surfaces. These don't mate. Unless you deform them, you couldn't make them mate. So this formed by a fundamentally different process, and it's also revealed by doing electron microscopy further onto the surface of those interior cavity surfaces. There are no voids. There are just serrated ledges indicating that this is discontinuous plastic slip along crystallographic slip planes that result in the separation of this material. This goes back to something that Orawan found in single crystal aluminum specimens called alternating slip mechanism. And we've been able to assemble this alternating slip mechanism to argue that that is what can create this rectangular cavity inside a polycrystalline copper specimen, but it has to be pure. If it has second phase particles or other impurities, it will destroy this mechanism completely. I'll talk about simulation of this in a few minutes, and also about additional measurements. The counterpart, the 6000 series aluminum alloy, again, the same thing, unload from A, the width of the specimen is here. You hardly see any evidence of necking at this point. The load has started to drop, localization has started to appear, but no change in the dimensions. At B or C, you see something like this. This is the neck that forms. And eventually at E, it fails, but this time the failure is somewhat different from what we saw in the copper. Again, there is plane strain localization, and so these bands along which the failure occurs are localized along that orientation. But they fail by a different mechanism. If you look on the surfaces of those fractures, they're fully dimpled. They say that there's a void growth and coalescence mechanism by which this occurs. If you look at specimens that are just before the point E, you don't see any cavities. What that means is all of this part of the response is driven simply by plasticity and not by any damage mechanism. Damage occurs at the very tail end, and we've been able to prove this through X-ray measurements that I was planning to talk about, but I don't have time. But they form at the very tail end of when the material is about to break, and furthermore, they're highly localized. If you make a section along this line and see just below the surface, how far below the surface do these dimples form? This is the surface of the fracture. These are sections below the surface. And if you go about 1 grain diameter or so, there's no more damage anywhere. So damage occurs late in the game. And I'll define what I mean by late in the game is in a few minutes. And it occurs in a very localized manner. The rest is all plasticity. So what more can we diagnose? How much more can we extract from the experiment? These are images of the copper grain prior to the loading, and on the right-hand side, after the loading, when the specimen has failed. And you can see grains that were about 20 or so microns in width have now gone to something that are about 2 to 4 microns in width. They've elongated significantly, roughly 10 times their initial length, and decreased in. So the strain levels here can be measured simply by looking at grain statistics before loading and grain statistics after loading on a point or a region-wide basis. And these strain levels are enormous. They're on the order of, so this is how you calculate the strain, but I'll go by that. Strain levels locally are on the order of 2 to 3 without any damage. This is pure copper, and it can go to such strain levels. So if you want to use a strain to failure criterion, making global measurements are almost irrelevant because locally the specimen does something completely different. And we've been able to observe local strain levels on the order of 3 to 3.5 with moderate triaxialities and about 2.5 with high triaxialities without failure. This is what I mean by late in the game. You have to allow the material to strain to such levels and therefore develop constitutive models applicable to such strain levels before fracture occurs at all. Corresponding measurements for the aluminum alloy, grain structure prior to deformation, grain structure after deformation, and you can see strain levels are on the order of 1 to 1.5. Again, globally calibrated strain to failure criterion, locally calibrated strain to failure criterion. These seem to work very well and in a predictive manner. And I'm running out of time, so I'm going to show just one computational result. This was done by Andrew Gross in the first Sandia challenge. If we use this idea that the local strain to failure is extremely high, we're able to do predictions. The blind prediction is the black line, the experiment is the red line. We're able to do reasonably well first Sandia challenge, second Sandia challenge. It's still essential to calibrate these strain to failure criteria appropriately through direct measurements. Here we did not have those measurements, so these were indirect calibrations, but that's something to keep in mind for the future work. All right, the last one is one Oscar made a reference to. It's been a pleasure to work with Oscar in these things. We've had, I would say, fights over what constitutes failure and appropriate failure criteria. They have not stopped yet. We're still fighting. But this one was a very interesting experiment. It's a recreation of something that Gent worked on starting in the 1950s in PDMS specimens. If you make the specimens badly, this is a PDMS that has a bead embedded, glass bead embedded inside of it. If you made the specimen badly, poorly, the bead will separate from the PDMS and you'll see a debonding, and that's not a desirable thing. So you go through special processes of tailoring the surface so that you have very strong interface and there's no interfacial debonding. Then cavities pop in the bulk, and this is an important nucleation problem because this is the starting of failure in these materials. He performed an experiment in 1984 where he had 2 beads confining the region in between them and tried to obtain images of what happens as a function of the global strain between the 2 beads. And he found that some things happened near the poles of the beads, but then something transitioned and occurred in the midline between the 2 pieces, which turned out to be a crack. There are multiple explanations for this thing, and I don't have time to go through all of them. One is that it is an elastic instability of a spherical cavity in a neo-Hookean material. And there are bifurcation calculations to show that if the pressure level reaches 5/2 of the shear modulus of the material, a small cavity will grow in an unrestrained manner. Max Williams, my academic grandfather, had a different idea where he introduced the idea that fracture energy on the surface must be accounted for, but he still worked on this within the framework of a neo-Hookean material. And so the neo-Hookean instability still was at the limiting part of this picture of fracture. The basic question is this cavitation and its growth a deformation problem leading from instability, or is it a fracture problem leading from surface growth? So new experiments, new diagnostics are needed in order to accomplish this. So we did experiments on the same material. Dow Chemical seems to make something that's very consistent over decades. With the nominal composition that everybody uses, we also recognize that you could play with this elastic stiffness and the stretchability of the polymer by varying the composition to non-recommended stoichiometric cases. And what this means is at a 45 resin to 1 catalyst, there are fewer crosslinks in the material than in the nominal 10 to 1. And therefore, it's going to exhibit much more stretching before it starts to stiffen up. And you can see that in the uniaxial stress strain curve. The 10 to 1 has a very low amount of stretchability, stiffens up almost near a stretch of 2, whereas a 45 to 1 will go to about 5 or 6 before it starts to stiffen up. And that has an impact on when these cavitation instabilities, etc., will occur. All right. The experiment is very simple. You cast the PDMS, this is the gray shaded region, between two rigid blocks of a polymer bead, treated suitably to get very good adhesion. I'm running out of time. So all we did was put this in the bay of a microscope at high magnification, put a video camera on it at 50 frames per second to be able to time resolve, and then run the experiment. And I will just play this video. So these are the two beads. This PDMS is in between here and is getting stretched. And what you see is popping of cavities from the inside. These are not at the surface. You can see a gap between them. And they are only visible because they occlude light that's being transmitted from below. And you can see there's a stochasticity to this. There are different nuclei that get popped up at different time instants, meaning at different global or local stretch levels. And they don't interact with each other. They don't coalesce. Some of them have grown to very large extents. And you could very easily visualize that these are penny-shaped cracks that if you unload them, they will go back and coalesce with each other. The two surfaces will go back to each other. All right. So a very simple estimate of the size of the cavity when they first pop is it's about 10 microns. Initially, the defects are no larger than about 1/10 of a micron, because if they are larger than that, they'd be visible optically, but they're not seen in these images. So we assume that the largest possible flaw there is on the order of 0.1 micron, which means there is a factor of 100 between them. So the approximate guess for a stretch is about 100. This is physically unrealistic. No material, no PDMS is going to stretch to a factor of 100. So even when we see the first object that's there, it's not a cavity, but it's a crack. So fracture is an essential part. If you look at a later stage, the picture is even more dire. Stretches are on the order of 1,000. This really is a crack, and we've been able to show that by unloading it and looking at that. I want to skip all of these things and go to one final picture, which is something that happened serendipitously. We unloaded the specimen and found that these cavities were closing back up. And I'll show this by one experiment. The red line, small line, is the initial distance between the two. We stretch them. Somewhere about there, there's a cavity that pops from the right-hand side, and then we unload it. So now we're going to start unloading. We unload it back to the original place and hold it there. The black spot disappeared, which means the cavity has closed. If it is a cavity and you reload it, you expect that it would open up. So we reloaded, it hasn't opened up at all. more than that. We reload it to the same place where it was before, where the cavity from the right-hand side had popped. It hasn't grown. If you go even further there, it pops, but this time from the other side. So the first cavity that formed was healed. Not only was it was healed to be stronger than what it was originally. Interesting thing to talk about, and Oscar and I have been figuring out or arguing how to make this thing work. We've done a number of cycles of loading and unloading. Each time it seems to get stronger, but with some kind of a saturation. So we're dealing with statistics of defects that are nucleating these cavities, and there's a large problem to be explored here further. All right, with that, I'm going to close. I think I took a little bit longer than I anticipated, but I want to close with a quotation from Tresca, another pioneer experimental scientist, who says that this work has not been done as a result of preconceived ideas and as an end we propose to reach from the first. It has presented itself to us only in consequence of varied experiments, realized in the first place in complicated circumstances, which we have striven to reduce more and more to conditions which are simple and such as to permit the laws of the phenomenon to be studied easily. This is the essence of discovery experiments. You do many of them. You don't know ahead of time which one's going to succeed. You refine them until you find that simple experiment which says, aha, I know what's going on. With that, let me stop, show you a picture that I didn't talk about because I like it. It's a heterogeneous deformation and failure in an elastic plastic material. Thanks for your patience in listening to this, and I'm open to questions. Thank you.